now let's continue and talk a little bit about our second sorting algorithm, which is going to be quicksort. So again, this is going to be the same type of divide and conquer approach. So, right, I want to start here with the rough idea. So this is again divide and conquer. So again, we're going to be kind of breaking our list into two pieces. Again, we're going to be then kind of recursively sorting those two pieces here. But the kind of general idea is a little bit different in this case. So let's think here of our list again. So suppose I have 5, 1, 2, 6, and then we have 7, and then 4, 3, and 8. So this is my sorted list, or this is my list in this case that we're going to be kind of working with here. Now, again, I want to start with a rough idea in this case. And so the idea of quicksort is you start by picking a pivot value. Now, this is something that a lot of details can be done with. We'll talk more about the details, but a lot of times you'll just pick the first element. So our first step here is kind of starting by picking a pivot element. And often you will use the first element of the list. We'll talk a little bit more about this later, but kind of not too much here about that right now. These are definitely things you can do to optimize the quicksort and kind of stuff like that as well. So as we're kind of explaining this, see if you can think about problems that can happen with the pivot element. But right, you can't see any problems yet because I haven't told you what the pivot element does. But the idea here then is that we use the pivot element, or use the value of the pivot element, to split the list into two pieces, right? So then using this pivot element, divide the list into kind of greater than the pivot element and less than the pivot element. And just for completeness here, right, we could always change these. What happens if we have ties, stuff like that, right? So those things don't really matter. But yeah, maybe for completeness, right, some of the list is going to be bigger than the pivot element. Some of the list is going to be smaller than the pivot element. Now, I want to kind of gloss over this idea right now, right? This is called partitioning, right? We call this step partitioning. And it can be done in O of n time. So that's kind of our idea of this. So the rough idea of quicksort is you take this pivot, we take our kind of pivot element, and then, right, what's going to happen with our partitioning step. So we take our whole list, right, and when we do the partitioning, so our partitioning is going to be done. And again, I'm not giving you the exact results of this partitioning or the exact details of the partitioning yet. We're going to talk about those in a couple of minutes. But the general idea then is we divide our list, right, in some way. It doesn't need to be exactly the result I have here, but in some way we end up with the smaller elements on one side. So let me just write it as 1, 2, 4, 3. And then we have 6, 7, 8 here. And now we're left with these two sets, right? These two smaller portions of elements. We have our 1, 2, 4, 3 and our 6, 7, 8. By now, we should have a pretty good idea of what's coming next, right? What's coming next here is that we're going to recursively sort both of these pieces, right? Recursively sort these pieces next. And you can do that the same way as well, right? So you find a pivot value, put it in the kind of two divisions with this partition step, and we're kind of breaking stuff down that way. I didn't make it kind of clear in this case, but it should be easier to kind of visualize. This could probably be done in place. We probably don't need to build a new list, right? Now, the 5 is in the right spot, right? So I want to point out here that this 5 is now good, right? Let me put a star by the 5. The 5 does not need to move anymore. We already know that all the elements before it are smaller than it. All the elements after it are greater than it. Maybe those portions will need to be messed with, but they don't need to touch the 5. They don't need to cross over the 5, right? We've now split it into these smaller pieces that we can deal with totally separately from there. And so that's kind of the rough idea again. So to summarize this a little bit, we have then for the analysis here, we partitioned the list into two parts based on this pivot value. We're going to talk about those details in a second, but to kind of talk about this here, right, this can be done in O of n time. So there's no issues with the partitioning. We can sort that partition in O of n time. And then we recursively sort the two parts of the list. Now, this is where stuff gets a little bit complicated. So looking down a little bit, you can see some things can go wrong here. We would like to say this is O of log n. right? Your general conception, if you do this on average, it's kind of like merge sort, right? We divide it into two parts. We divide it into two parts, right? And then we recursively kind of sort those two parts there. What is our caution though? What is the issue when we're dealing with quicksort here, right? Caution, right? Because we're using pivot values, we don't actually know we are dividing the list equally into two parts, right? So what is the kind of worry of stuff here? When we were doing merge sort, how did we divide it into two pieces? Well, we just cut it literally in half, right? Maybe they were odd and even if we had an odd number to start with, but in general, right, we did our divided by 2. Here's the one portion you now sort, here's the other portion. That definitely is a log n, right? Dividing into two equal pieces each time, right? We don't actually know that's the case here, right? In the previous example, 5 was our pivot value. So we had 1, 2, 3, 4 on one side and 6, 7, 8 on the other. So that one worked out nicely. But what if we have different pivot values, right? These are kind of leading to cases where this can devolve into O of n. This kind of division can become O of n in the worst case. So in other words, we actually do end up with a O of n squared in the worst case here. So in some scenarios, this, as far as big O notation is concerned, is no better than a bubble sort or an insertion sort, things like that. On average, it works out, right? So you kind of pick the pivot value, right? You can kind of worry about those types of things. You can, however, do some tricks. There are some tricks that improve the kind of likelihood you end up in a worst case, right, to make it slightly better. But there's no getting away from, in the worst case scenario, this is O of n squared. So just as kind of a quick example of this, right, what is a scenario where we kind of end up in the worst case? Well, even the case where it's actually already sorted or sorted in reverse is kind of the worst case. So, right, maybe let's not do the full example here. And let me even show that kind of even it can be worst case in kind of single portions or kind of stuff like that as well. So suppose even we have kind of 8, 7, 1, 2, 3, 4, 5, 6. So the issue here is that the pivot value, right? And this might not happen all of the time in this case, but in a single step, the worst case is that the pivot value is the largest or the smallest, right? So the worst case scenario is when the pivot value is the largest or the smallest. So why is this the worst case? Well, let's think about what happens here. How do we partition our list, right? What's being done in the partition? Well, when we partition this, we actually end up with just one element being, we don't even end up with two lists, right? We end up with 7, 1, 2, 3, 4, 5, 6. Of course, our 8 is here. And then we have an empty list on the other side, right? So in this worst case scenario, we partition. So our partition ends up with right? We end up with 7 and 0. So this is no longer an even divided by 2, right? Our recursive portion doesn't really help us here. This is just like doing a single pass to put the 8 at the top, right? And so now even if 7 was at the front, again, we would now have a list of size 6 and an empty list, right? So this is the kind of breakdown when we use these pivot values, our kind of trade-off from being able to do this without moving kind of extra storage, needing extra storage like we did in merge sort and stuff as well. So with that kind of worst case in mind, right? Of course, on average, this will be roughly dividing the list in 2. As long as you're roughly dividing it in 2, you will recover that kind of log n portion of the runtime. What are we missing from the actual kind of runtime analysis? What are we missing from kind of our kind of pieces in this case? Well, remember, we still need to worry about our partition details, right? So I want to just kind of focus here on how do you end up doing the partition in this case. So what's kind of going to happen here? So let me write out my list. It's good to have a number, I think kind of like I did before, like 5 in the kind of middle here. So we have 2, we have kind of, let's say 7, then we have 3, 8, 6, and then let's say we have 1 and we have 4. So again, there's kind of different ways to look at this, right? There's different ways to go about thinking about choosing the pivot values, and there would be different ways to do this partition. But let's kind of focus on one specific kind of way of doing this. So we have our kind of pivot value. So that is one important thing we want to look at. And then what we're going to be thinking about here, and the usual way, actually let me use a different color for the pivot value so I can kind of use more standard colors next. We're going to be looking here then at what we want to call kind of the left mark and what we want to call the right mark. So I'm going to call these kind of two pieces the kind of left and right marks. So our blue is now here the left mark, and then red is going to be our right mark in this case. And what we're kind of doing, and again, this kind of is done in a loop. So of course, this is our kind of O of n kind of stages here. But we always kind of want to look at what is happening in terms of the two marks. So for the blue mark, right, what is okay, right, being less than, right, the pivot, and bad is being greater than the pivot. So, right, for the blue ones, again, maybe let me say okay is less than or equal to the pivot, bad is being kind of greater than the pivot. For our right mark, of course, this is kind of in reverse, right? So okay here is being greater than or equal to the pivot value, and bad is being less than the pivot value in this case. So what we kind of do is, right, during a single step, right? So in a single step, right, we search for the first set of bad positions. So what do I kind of mean by this, right? We search both for both the left, right, both for the left and right marks. We search for the first set of kind of bad positions. So the first kind of places where something is going wrong. So is the 2 okay? The 2 is fine, right? So we move on. Is the 7 okay? No, right? So if we kind of do this in our kind of first step, right, this one was okay, this one was bad, right? Is the 4 okay? Well, immediately the 4 is not okay. So now we look for our first kind of set of bad positions here. When we find the first set of bad positions, right, then we swap those positions and continue / repeat, right? So it's not really repeating because we don't start over from the beginning again. But right, what I mean is repeat, we keep doing this kind of search for a bad position. So I found the 7 and the 4, so I want to swap those two positions here. And now, right, these are actually immediately seen to no longer be bad positions, right? Immediately at this point, right? And I'm not really going to continue doing our check marks and stuff along the way, but immediately now we know the 7 and the 4 are okay. So we move on to the 3, that is okay. We move on to the 6, that is not okay. Now, 7 is now automatically okay. We move to the 1, that is not okay. We've now found bad positions for the left and for the right. So, right, now we again do a swap. So here we kind of have an 8, and then our 1 get moved that way as well. Okay, so we now move our 1. So here is what we need to be careful with at the end. So we move our 1. 6 is now a bad position. Now, what about the red? The red we search. 6 is okay, 1 is bad. Now, in our last set of bad positions here, what do we notice, right? So note, at the last step, the pivots or the marks cross. Now, what does it mean when the marks cross? Well, this means now we're done, right? At this point, we swap the right mark. So then, right, we swap the right mark with pivot, and we are done. So this is our kind of last step in this case. So once they cross, notice here, 6, 8, 7 are now all bigger than 5, right? 1, 2, 1, or sorry, 2, 4, 3, 1 are all less than 5. So as our final swap, we can say, okay, we take our pivot value, right? It's no longer special there at the beginning, but now we have our 5 in the middle, and then it's partitioning into the two pieces, right? We now have our left side over here. These are all the smaller values, and now we have the right side over here with all the larger values. So this is kind of our division of the set into our two pieces from there. That's kind of walking through what we have as far as these partition details. And then, of course, you recursively run the quicksort on the blue portion and the red portion, right? So that's kind of exactly what we're doing then to finish things up there. Okay, so summary of these two kind of sorting methods as well. So they're both often O of n log n, right? So these are oftentimes referred to as these kind of O of n log n methods. They both rely on this divide and conquer, and this divide is what's giving us the log n. So what are some extra comparisons or kind of, contrasts between the two of them, right? Merge sort requires this extra space. When you're doing the merging of the sorted lists, you're building this auxiliary list to hold stuff. You need that extra space memory to be doing that. So that is not feasible in certain scenarios and kind of adds some messiness to that sorting algorithm. You don't need any of that in quicksort, right? You can always be splitting stuff up, right? Moving things around in place, swapping elements of the list, etc. But the trade-off is, in certain cases, it can be O of n squared. There are ways you can mitigate that, make that less likely to occur, but in these kind of worst case scenarios or bad cases, it's going to be kind of O of n squared in that scenario. So that kind of is a negative of that one there. Now, our natural question always here is, can we do better? Unfortunately, in a very real way, this is kind of where things stop. In general, a runtime of O of n log n is optimal, right? So what this kind of means is there are kind of quote unquote proofs of this, where if you're looking at specific scenarios, we're comparing numbers, right, with no restrictions, we're comparing words, alphabetical words. In a very real way, if you're looking at like comparisons, how many comparisons do we need? You can't do better than n log n. That being said, these rules are always meant to be broken. If you know additional information, you can sometimes beat n log n. So there are cases where you can get O of n sorting techniques. But these are kind of specific cases there, right? We really mean additional information is known. This is going to be talked about more in kind of the next section, right? But in general, if you say want to be able to sort a list of numbers where the numbers could be, right, as small as we want, as big as we want, in general, you're not going to beat n log n. But if you have specific info, extra info, you might be able to do better in these kind of specific cases from there. Okay, so that will bring us to the end of this n log n sorting video, right? Of course, we're lying a little bit with quicksort, but that kind of is often thought of as an n log n sorting method and actually is used in a lot of cases as well to kind of deal with sorting methods. It's easier a lot of the times because it can do that sorting in place and stuff like that fairly naturally. But in the next video, we'll be exploring some of these special cases, these special scenarios where you can actually do linear time sorting as well. So hope to see you then, but goodbye for now. Thanks for watching.